So today I want to introduce you to the signal flow graph. The signal flow graph is in principle a graphical representation of the equations of the S parameters. As graphical elements we use nodes, and the nodes are used to denote wave amplitudes like A, E or BE. We use this to describe the wave amplitudes, and errors are used to denote the S parameters. As an example, I want to discuss here first, for example, one port, and we know that up to now we sketched it like this. We had A1 is entering the one port, and B1 is the reflected wave amplitude in principle of the one port. But now if we use the nodes and the errors, we can set up the flow graph of our one port, and we say this is the wave amplitude A1, this node, and then we have here the wave amplitude B1, and S11 is connecting the both nodes, and you see now according to this, B1 is nothing else but S11 times A1. So B1 is equal to S11 times A1. So we see here this signal flow graph is nothing else but the graphical representation of this equation. We can extend this also to a two-port. In a two-port we have four wave amplitudes, so we have here A1 and B1. They correspond to port 1 here, and we have here, for example, the wave amplitude B2 and A2. They correspond to port 2. And then we know, for example, that the A1 times S11 will contribute to B1, so here we have the parameter S11, and the transmission factor S21 will contribute to the wave amplitude B2. The same is true for this, so we have here S22, and here we have the parameter S12. So to get the equation describing a two-port, we just have to look at the node, and we see here that B1 is given by the addition of S11 times A1 plus now S12 times A2. And we can have a look to the wave amplitude B2. B2 is then given as S21. You see here B2 is the addition of the two errors here as S21 times A1 plus S22 times A2. So what I did here is now I introduced in principle the so-called signal flow graph, and now I will give, in the next step, I will give you the signal flow graph of certain elements so that we can set up in the last step a measurement system for S parameters. I want to introduce now special devices and their graphical representation, and as a first device, of course, if we want to set up a certain measurement system, we need a generator. So in principle this is a one port, which will provide a certain wave amplitude, and we can sketch it in principle like this, that we have here A1, B1, here A0. The generator will generate this wave amplitude A0, and I assume it will feed this to B1, and here we will have the wave amplitude A1. And if we have a generator in a 50 ohm system, of course, and then here we would have the parameter S11 to be 0. Of course, a generator can also have a certain input reflection coefficient. As a further element, we will discuss here a lossless transmission line. The lossless transmission line is in principle a two-part, and for example, sometimes if it's a coaxial transmission line, its cross-section is sketched here, and we will have here the wave amplitude A1, B2, B1, A2, and in between the two waves. So we already know that the transmission line is an element free of self-reflection. Here we will just have the exponential from minus j beta times L, which describes the phase shift due to the transmission line. A special application further is a so-called one-way TL, one-way transmission line. These are special transmission lines which are used to protect the generator against reflections. So in principle we again have here the wave amplitudes A1, B1, here B2, A2, and in the ideal case this will just the one-way transmission line will introduce a certain phase shift phi, depending on the length of the transmission line, but it will show no losses. But all other parameters will not exist. So especially S11 will be 0. Also here the parameter S22 will be 0, and also there will be no no transmission from port 2 to port 1, so S12 will also be 0. This is an ideal one-way transmission line. A further element could be an absorber. It's sketched like this. An absorber is in principle a one-part, and here you have the wave amplitudes A1, for example B1, and if we have an ideal absorber, then the reflection S11 would be 0. What we further need is some equipment to measure the wave amplitudes, and I will sketch it like this. So, for example, we could use an absorber, a special absorber, which is able to measure a certain wave amplitude. For example, here we could say this is A1, B1, and if we have an ideal absorber, of course, then S11 is equal to 0, but I want to assume that this measurement equipment is able to give us the wave amplitude A1 by absolute value and phase. In the next step I want to introduce the so-called directional coupler. I want to introduce now a directional coupler. A directional coupler consists in principle of two transmission lines, and I assume here that these transmission lines identical, so we will have a transmission from port 1 to port 2 and from port 2 to port 1. So we will describe this by a so-called transmission coefficient, and we assume that the transmission from port 3 to port 4 and from port 4 to port 3 is identical, is also described by a transmission. Now there exist different kinds of directional coupler. One of the kind of directional coupler are directional coupler which are built with the help of rectangular waveguides or waveguides. So they normally couple in this direction. So port 1 and port 3, port 1 couples to port 3 and vice versa. So we will have here a coupling now from port 1 to port 3, and we will have a coupling from port 3 to port 1, and we will assume that we have the same coupling between port 2 and port 4, and we will have a coupling between port 4 and port 2. This we will denote by a coupling coefficient C. As a transmission line, always the input reflection coefficient of the transmission lines will be 0. If I set up the S matrix of a directional coupler now, we assume that this is an ideal directional coupler, though the transmission lines will be free of self-reflection. That means here we will always have a 0, and then we will have, for example, again here the transmission between port 2 and port 1, though here we have a transmission coefficient, and we will have a transmission between port 1 and port 2, the same transmission coefficient. We will have a transmission between port 3 and port 4, though here we will have the T, and we will have a transmission between port 4 and port 3. Also here we will have a T, and the coupling will occur between port 3, perhaps I start with port 1. Port 1 to port 3 we will have a coupling C, and we will have a coupling between port 2 and port 4, and we will have a coupling between port 3 and port 1, and we will have a coupling between port 4 and port 2, though here are always the same coupling coefficients. And what is very important here is now in the ideal directional coupler we will have no coupling between port 1 and port 4. So here we will have a 0, here we will have a 0, here we will have a 0, and here we will have a 0. So this is the S matrix of an ideal directional coupler, and of course we can also apply here, if I assume that lossless, lossless directional coupler, according to our equation, we must say that the absolute value of T square plus the absolute value of C square will be 1, or I can in principle calculate the absolute value of the transmission coefficient. It will be equal to 1 minus the absolute value of the coupling coefficient. So you see, even if I assume a lossless directional coupler, a part of the energy, if I couple a part of the energy, for example, from port 1 to port 3, then of course the transmission between port 1 and port 2 will be reduced. So this is the S matrix of an ideal directional coupler. I want to discuss now with you the principal setup of a reflectometer. The purpose of the reflectometer is to measure the reflection coefficient of our load here, or it's sometimes called dart device under test. And what we need to measure this, the reflection coefficient of this device under test, is of course first the generator. To protect the generator we use a one-way transmission line, and the essential element will be our directional coupler. Now I just want to sketch now the signal passes which are relevant. So in our generator, the generator will generate a wave amplitude A0, and we will assume that this is feed to the out of this generator, and also I assume here that we have a principal lossless one-way transmission line and I will assume that it does not introduce any phase shift, so this is not very does not restrict the things. So now we are here in the directional coupler, so we will have two things. One thing will be that the directional coupler will feed a signal to our reflection coefficient, but a part of the signal is also fed to via the coupling coefficient to port 3 of the directional coupler. Here we have the coupling coefficient C, and our load reflection coefficient will now generate a reflection. Of course, this generated reflection will be fed back also in the direction of our generator, but the generator will be protected by our one-way transmission line. But the further part will be now coupled to port 4. So in principle you can see now we can easily calculate the wave amplitude. So I assume here we could measure these wave amplitudes. So we would measure then B3. According to this, you see in principle B3 will be C, the coupling coefficient, times 1 times 1 times A0. So the wave amplitude B3 will be proportional to A0, the generated wave amplitude of the by the generator. And if I assume now B4, then you see B4 according to this will be equal to C times, here we would have in principle B2 and here A2, but B2 is RL times A2, so here we will have the load reflection coefficient, and then we have again T times A0. So this will be the wave amplitude B4, and this will be the wave amplitude B3. Now I assume that I can measure both wave amplitudes by absolute value and phase, and we will define the measured reflection coefficient Rm. You see here I will define this as B3 over B4, and now you see here we will have, oh sorry, this is B4 over B3, and this will be C times T times RL times A naught divided by C times A naught. And you see, this will cancel against this will cancel against this, and we will get the measured reflection coefficient will be T times the reflection coefficient of our load. You see here that the transmission factor T introduces a systematic error. And as soon as we have a systematic error, we can discuss a so-called calibration to get rid of the systematic error. Of course, if I have only one systematic error, I will only need one calibration step, though this I will explain in a further step. We saw here that even if we use an ideal directional coupler, this ideal directional coupler will introduce one systematic error into the measurement of a load reflection coefficient. To correct for this error, we must in principle do a calibration process, and the calibration process is like this. To correct for one error parameter, we need one calibration standard. For example, we can need, in the first step, we use a load resistance, a load reflection coefficient of -1, which means a short circuit. Well, just write short here. So in the first step we can measure the calibration standard, so RMS will be then minus T, or we find that T will be minus RMS. And in the second step we do the measurement, and if we measure, then we find that Rm is again T times RL, and we can in the third step do the correction . This means, since we measured with we measured the known reflection coefficient, then we can in principle calculate the transmission factor, and from this equation we found that RL is equal to 1 over T times Rm, which is equal to 1 over minus RMS times Rm. This means now RL will be equal to minus 1 minus RMS times the measured reflection coefficient RL. So I want to repeat this or summarize this again. So we see, even if we use a ideal directional coupler, the ideal directional coupler will introduce one error parameter. In this case it will be the transmission factor T, and of course this depends on, it has a different absolute value and phase, and we must figure out its absolute value and phase. To do this, we in the first step measure a calibration standard. In our example we use the short circuit, and in principle now we measure this calibration standard, Then we do the measurement again, and then in a third step we do the correction. So of course you have to do this for each frequency step you want to measure our reflection coefficient of our load. So you have to do a complex to solve for a complex valued equation. I want to discuss now what happens if I assume that I have a directional coupler with so-called find isolation. At the moment we assume that we have an infinite isolation. This means if I insert a wave amplitude into port 1 of the directional coupler, there will be no coupling to port 4. This in principle corresponds to an infinite isolation. And now I want to assume that we have a further error. This means I will assume that even so, if I just insert a wave amplitude into port 1, there will be a very small part of the wave amplitude will be fed to port 4. So we will, as equations, we will get then for B3, the equation will not change. So B3, we will still have that this is C times A naught, but in the equation for B4 we will have a different form now. Of course we still will have C times T times RL times A naught. So this is the path we want to have, but now I assume that there is an additional path, so we will have plus epsilon times A naught. So I just assume that this value will have, epsilon will be a very small value. So if I again define now our measured reflection coefficient as B3 over B4, then we will have that C times T times RL times A naught plus epsilon times A naught divided by C times A naught. So for the measured reflection coefficient we will get that this is, of course, here, this will cancel, so we will have our original term T times RL, but there will exist now an additional term epsilon divided by C times A naught will cancel. So you see, especially for a low reflection coefficient of the load, if this is, for example, 0, then due to the find isolation we will still measure a certain reflection coefficient here. And normally we will, though this ratio will determine the lowest absolute value of reflection coefficient which can be measured, and this is normally denoted as the, I have to look here, directivity of our DC. The directivity of our directional coupler normally is denoted as AD is minus 20 log absolute value of epsilon divided by absolute value of C. This is normally denoted the so-called directivity of a directional coupler, and it determines the lowest reflection coefficient which can be measured without correction. If I would use now the normal notation for S parameters, I could write this is minus 20 log the absolute value of S for 1 divided by the absolute value of S 3, 1. So this is of course here this is the definition of the directivity of a directional coupler, which determines the lowest reflection coefficient which can be measured without, in principle, of correction. I want to discuss now with you the so-called one-port error model. So I sketched here a real reflectometer. I omitted the one-wave transmission line, and I assume that I can measure B naught and A naught, and we define the measured reflection coefficient as B naught over A naught. But we assume that this is a real reflectometer with different errors, and now we assume that we can locate all the errors in a so-called error two-port. This is our error two-port, and we assume this to be the ideal reflectometer, so that we get now this error two-port. So we will have here the measured wave amplitudes, or realized wave amplitude B naught and A naught and B naught. But here we assume that between the measured reflection coefficient and the reflection coefficient of our load, RL, so-called error parameters are introduced. So we will have here, for example, the parameter E. So this is a transmission from 0 to 1, and here we will have the transmission from E 1 to 0, and here I assume to have a parameter E11, and here we assume to have a parameter E22. So this is the so-called error parameter. Here we have B1, and here we have A1. So to calculate now the measured reflection coefficient, we must calculate B naught. According to our setup, we see B naught, it's at E11 times, oh sorry, I used different indices here, so I have here to use 0, 0, and here 1, 1. So we will get here the wave amplitude E00 times A naught plus, you see here, E01 times A1, but we will see that A1 is given by RL times B1, while B1 again is given by, I can write here, B1 will be given by E10 times A naught plus E11 times A1. So we can see that A1 is given by RL times E11 times A naught plus RL times E11 times A1. So we have here A1 in one equation, so we can get this. On the other side we get A1 times 1 minus RL times E11 will be equal to RL times E10 times E0. So from this we find that A1 will be equal to RL times E10 divided by 1 minus RL E11 times A0. Of course, this can now be inserted here. We get, so here B0 will be E11 plus, and here we will have E01 times E10 divided by 1 minus RL times E1, perhaps I'll write it in this way, E11 times RL times A0. So for the measured reflection coefficient, we get this is B0 over A0, and we get for the measured reflection coefficient is E10 plus E11 times E0 divided by 1 minus E11 times RL times RL. So we see here, this is now our measured reflection coefficient, and if I use this so-called one-port error model, then we introduce all the errors in a two-port here, and this will result in 3 different error parameters. And this error parameter, and this means to get rid of or to do the correction for the 3 error parameters, we need 3 calibration standards, and this we will discuss in the next step. So I want to discuss now the so-called open short load calibration, or OSL calibration comes from open, short and load. According to our one-port error model, we saw that the measured reflection coefficient is not, of course, not equal to the load reflection coefficient, and there are 3 independent error parameters. This here only the product of the two, and this, so we have 3 error. This means we need 3 calibration standards. Three calibration standard, and one possibility to do this is the so-called open short load calibration. So we do, for example, we can start with the load measurement, and if I have a load measurement, then I assume that RL is identical to 0, and we see that we would measure then RML, it's E10. We can do, for example, as a next step, the short measurement. In the case of an ideal short, our load would be RL is -1, and so we get a parameter, a measured parameter, RMS I call. According to this equation, this will be E10 times here, RL is -1, so we have here a -1, E10 times E10 divided by 1 plus E11, and we can, as a next step, do the open measurement. This means our load will be the ideal open. This means it will be 1, and we will have that we have RMO will be E00, and now we will have plus E1 0 times E0 1 divided by 1 minus E1 1. So in principle we can already insert this into the equation. So we have here RMS will be RML minus E1 0 times E0 1 plus E1 1, and we will have RMO will be RML plus E1 0 0 times E0 1 divided by 1 minus E1 1. So in principle we have here two equations for two unknown error parameters. This means we can solve for these two error parameters. So we will assume that E01 times E10 is known now, and we know that E11, which can be calculated from these values, and then we can do the correction. In the correction we just must solve this equation for RL, and we, in this case, we would get that RL is then RM, the measured minus E00 divided by E11 times RM minus E00 plus E10 times E01. So, to summarize this again, we see that if we assume a two-port error model, for our one-port error model, we can use the so-called OSL calibration. For example, if you want to measure a certain frequency range, then you will subdivide the frequency range, for example, in 100 steps. And for each step, you must measure the 3 calibration standards, which are in principle then 3 times the measurements. And if you measure the calibration standard, you can solve for the error parameter E00, and we can solve with the help of these two equations for these two error parameters. And this you have to do for all the steps you consider, for all frequency steps you have to consider, and later on you again do the correction for all frequency steps you have to do. You have to solve this equation, and this is normally done automatically in a so-called vector network analyzer.